ACI for, so we're gonna do it tomorrow.
Y'all are doing 3 different days.
We did Monday morning, Tuesday night, Wednesday morning, and Wednesday night. Thursday night to Friday morning. So that's 3 morning shifts and 3 afternoon shifts.
Okay. I thought it was supposed to all be on the same day.
I don't know. Josh is in charge of our group, so that's the way we're gonna do it.
He probably knows.
I mean, hell, even if we don't, he's never gonna know if the numbers are correct anyways.
I wonder how we're gonna have to figure out. Y'all are counting, like, the other day in transfer, we had like a number of how many left, straight, and right. Y'all aren't counting individually each term. You just counting the number that come through your intersection.
What do you mean?
Well,
we have 4 guys, one on each corner.
Right.
This guy will watch this section. This guy will watch this one. This guy will watch this one. This guy will watch that one.
So you're just counting one, number of like how many come through.
No, we're counting each one. How many turn right, how many turn left.
We haven't been doing that.
That's how we do it. I think you're.
Because what we're wanting is the peak hour density, right?
You might want the peak hour density and be able to recommend some changes to that intersection. Because like one of our problems is the right turn lane after 2 cars, it gets filled up. You can't it's all backed up. So I think that we're supposed to do it like that. I don't know my shoot is.
Count.
Oh, yeah. Did you already take transfer? Transfer 1. What did y'all ask him?
For your traffic count, like each person is designated a portion of the intersection. And does that person count each turn individually, or do you just count how many come through your on the road?
What do you mean?
Are you counting how many turn left, how many turn right, how many turn straight?
Well, it depends on how we split it up. Like we said at, I think it was Highland and Carroll.
That's what Sean was.
We were Highland.
You are?
Straight, turn, which way they're turning.
Yeah, so like if I was, which piece of paper? I'll go ahead.
Because when you get your crash diagrams, you're gonna see where the most crashes happen. Is it in the right turning lane, is it in the left turning lane?
Don't listen to Sarah. Sarah's.
I've already done it. What did I miss in foundations?
Huh? You skipped on it. These are the whole reason we weren't going to go to the thing this morning.
I know what you're saying.
You wanna know the truth? I woke up and I guess I didn't wake up. Could have sworn I saw an email saying classes canceled.
That review is all for the ACI test. Isn't it from like 8 to like 12? You didn't miss anything at all.
Y'all didn't go over the campus, did you?
It was literally just an introduction to retirement. It was stupid.
Yeah, I could have sworn I read classes canceled, but I know I was dreaming now that I'm up. Yeah.
It's in reasonable numbers. That's what we somewhat did. If we fell short or questioned anything, we threw in maybe 10 cars.
That's how, like, we had Nettleton and Red Bull, and I had the corner that now is a right-hand turning lane, northbound on Red Bull, because traffic's backed up so bad. I suggested that's not why they did it, but it just happened. It happened after our. So yeah, you need to count everything.
I mean, I'm sure you could just. You can just do it.
Divide my number by 3.
Well,
Just
next
do it.
time when you count for real, just
Kind of.
average it out from your other ones. A third went right, 2/3 went straight. Whatever.
Dang.
Like,
Looking nice today.
I'm always looking up.
You never wear a jacket like that? I haven't ever seen you wear that.
No, really?
Blazers
Really?
before.
I've never seen him wear a blazer. Ever.
No,
I
I
haven't
have.
tested to see what happens.
You have to remember, last semester I was only in here for half a semester and left.
Uh,
Last year.
I mean, where? I'm gonna go throw it on the ground.
I never seen wear blazers.
I can apply over 40,000 pounds of pressure on my jacket.
So what do you do when you're not here?
what do you mean?
Like, do you
He's here
No.
until like 7 o'clock at night.
every day?
No, not every day. Sometimes.
What do you do? What does your free time consist of?
Just sleep.
Sleep?
Yeah.
Don't you have
I go to the
children
gym.
now? You have children?
Yeah, I have.
You have children?
Hmm?
You have children?
Yeah, two.
What? Since when?
10 years. Since 10
I
years.
was like, what?
I never knew that.
No.
Yeah,
That's crazy. I didn't think you were old
it's
enough to have
10
kids.
years old.
He doesn't think you're old enough to
How old
have
are you?
kids.
Hmm?
How old are you?
38.
You do not look 38.
I'm gonna be 39 soon.
That's crazy. That's crazy. That's crazy.
I didn't go get my quiz back. Yeah, I think so. You have a wife? Yes?
Yes.
Yeah.
That's crazy.
He asked.
How long have y'all been married?
Hmm?
How long have you been married?
11 years.
11? Interesting. I really didn't know that about you.
You need to know your whole life
You,
story.
you never talk about it before class, like on syllabus day. You never talk about your lives. You just,
Should I
yeah.
talk about it?
I think that's cool to learn about my professor. Like Dr. Wong when he talks about whenever he was back home.
Oh, he
how stuff
loves,
was
Dr. Wong loves to talk about home.
Okay.
I think
During
it's- I
the
think
only
it's-
the first lecture, or
Yeah, like
Sometimes we can get him off on a run about his
yeah,
home
he'll do
life.
it one day. When they got him started right in the beginning of the lecture, and he just realized 30 minutes in we only had 10 minutes left of class, and so he just finished talking for an entire lecture without realizing it.
That's not the goal. We want to get to know you.
Yeah, I think it's interesting.
okay, we're gonna see if we finish today early. We can.
I think it'd be interesting to learn about your life.
Okay, so good morning, everyone. So today we're going to continue our lecture about the stiffness method. So this is the example that we solved last time. Okay, we had this beam, we had a force at one given point, and we were required to find the deflection and the reactions. Today, let's go ahead and solve another example. This example is a little bit different because what to do when you have an internal hinge. Okay, so let's see this example here to learn how to deal with an internal hinge. So another example here, we have a beam that looks like this.
This is 15.2.
Yes. So we have this beam, it's L, this point is A, this is B, this is C, and we have a moment here. So the magnitude of that moment is known, it's unknown, okay? It's a moment that is applied on that beam, and the beam has constant EI, so both members have the same EI factor. The same modulus of elasticity is the same moment of inertia. And what we're required to do here is that for the shown beam, we're required to calculate the support reactions, the support reaction at point C, and the angles of rotation at B. Okay, so that's this problem. So what's new about this problem? How to deal with this internal hinge? We have an internal hinge here at point B. Okay, so how to deal with this problem? Let's just follow the steps. Okay, that we did in the previous problem. If you have your previous problem, just follow the steps. Just tell me what are the steps that we did. Okay, it's always nice to have, you know, a procedure to follow. Okay, don't miss the procedure. What's the procedure? What's the first step that we did in the previous problem? Just open your lab.
You need to assign your
The notations,
So get the numbers.
number the nodes, number the members, number the degrees of freedom. Okay, so that's the first step, the notation. Okay, so we're not going to make anything different. Okay, so step one, the notations. So if this is my member here, or this is my problem, it looks like this. So how many members do we have here? We're going to put them in rectangle. We're going to label them. So I have two members. Member from A to B and then from B to C. Okay, this is A, B, C. So here we have two members. And how many nodes? One node, two nodes, and three nodes. So 3 nodes. Now, the degrees of freedom. We need to label the degrees of freedom. Okay? And we said when labeling the degrees of freedom, it's the best thing to do is to label the unknown degrees of freedom first. Okay? And that's the major difference, okay, that we have in this problem compared to the previous problem. Okay? Now, when we label the degrees of freedom, we have rotation and deflection. Okay, those are the degrees of freedom that can happen at one point. Okay, so to label the degrees of freedom here, the most important point that you have to understand, okay, that here at point B, this point can move downward, right? There's nothing preventing it from moving down, right? It can rotate, right? There is no fixed support. The fixed support is the only thing that prevents a point from rotating. So there is no fixed support here. So it can rotate, right? But in addition to this, it's an internal hinge. So it's like a ring, okay? So those two parts can rotate independently, okay? This part can rotate with an angle, and the other part can rotate with a completely different angle here. When it can rotate here, it can rotate like this, can be formed like this. As you see here, those are two different angles. It's not the same angle, okay? Because of the internal hinge. So that means that at that point, at point 2, okay, or at node 2, okay, we can actually have two rotations. Rotation here in member 1 and a different rotation at member 2. It's not the same rotation because there is no continuity in the member in terms of the, flexural. The hinge breaks the continuity, right? That's the hinge, okay? It's a point that can, both parts can rotate independently. There is no continuity here, okay? So that means that we have a rotation here. So we have 1 degree of freedom here, 1 rotation here, and another rotation here, and a deflection. The deflection is shared, both ends, okay? There is continuity in terms of the deflection. Okay, this part, when the deflection here in this member is, let's say, 1 inch, this one is 1 inch as well, right? It's the same point. So this is the 3rd degree of freedom. Okay? So that's what you have when you have an internal hinge. That's the new thing in this problem. Okay? That now at node 2, you don't only have 2 degrees of freedom, you have 3. 2 angles, theta b left and theta b right. They are not equal to each other. Okay? And the deflection. And then here we have a rotation here, so I'm going to label this the 4th degree of freedom. And the vertical deflection is the 5th. Here we have the vertical deflection as the 6th degree of freedom, and the rotation as the 7th degree of freedom. Okay? So generally for point 1 you have 2 degrees of freedom, vertical displacement and rotation. Vertical displacement here and rotation. Here you have vertical displacement, but because you have an internal hinge, you can have 2 rotations. That's the only thing that is new. In the previous problem, we didn't have this internal hinge in our previous problem. We just had vertical deflection, rotation, vertical deflection, rotation, vertical deflection, rotation. That's the general thing that you have, but once you have an internal hinge, that increases by 1. Okay? You have an additional rotation at the hinge, the internal hinge. Okay? So that's the major difference. If you miss this point, okay, then you're gonna just, do all the problem completely wrong. Okay? So here, how many degrees of freedom then we have here? How many degrees of freedom that we have? 7 degrees of freedom. So generally you would have 3 nodes, you're going to have 6, but the internal hinge add 1 to your degrees of freedom. Okay? So you have 7 degrees of freedom. Some of those degrees of freedom, okay, are known and some are unknown. So here, just to explain this so that when you study you just have this, the why you have 7, because you have an extra 1. You have an extra degree of freedom. The connection, why is that? The connection at node 2 is hinged joint. Therefore, theta b left is not equal to theta b right. This is theta b left, and this one is theta b right. Okay? So the 7 degrees of freedom, some of them are known and some are unknown. We have the unknown degrees of freedom. This one is unknown, this one is unknown, this one is unknown. The rotation here is unknown. So I have 4 of them being unknown. So 1, 2, 3, 4 are unknowns. Theta b, the first degree of freedom represents theta b left. The second degree of freedom is theta b right. The third degree of freedom is delta at point B. The fourth degree of freedom is theta at C. And those are unknowns. You don't know any one of those. Theta, you don't know how much is theta b left, theta b right, delta b, and theta c. You don't know those. Okay? While the 5th and the 6th and the 7th, those are known. The 5th represents the deflection at point C. The 6th represents the deflection at point A. The 7th represents the rotation at point A. And those are equal to 0. So they are known. You know their magnitude. They are 0. Why are they 0? The deflection here, because of this support prevents the vertical deflection, so the deflection here is 0. The deflection here, you have fixed support, so it prevents the vertical displacement, which is the 6th degree of freedom, that's 0. You have fixed support here that prevents the rotation, so the 7th degree of freedom is 0. The rotation at point A is 0, theta A is 0. Okay? So those are your degrees of freedom. I have 7, 4 of them are unknowns, and 3 are knowns. Okay? Now, what's the next step? Just see, what's the next step that we did in the previous problem?
The stiffness matrix.
Okay, so the stiffness matrices for each member. Okay? How many members do I have here? 2. So I have to build each member stiffness matrix. Okay? So step 2, build each member's stiffness matrix. How to do this? I have 2 members. So for member 1, I'm just going to name it K1. Okay? You just have to copy this. Okay? You don't have to memorize it. I will give it to you on the test. Okay? The stiffness matrix for an element, it's a 4 by 4. Okay? How does it look like? It's 12 divided, so it's 12 EI, so I'm taking EI as a common factor, divided by L cubed. Here I have 6 divided by L squared, negative 12 divided by L cubed, 6 divided by L squared, 6 divided by L squared, negative 12 divided by L cubed, 6 divided by L squared. And then here you have 4 divided by L, negative 6 divided by L squared, 2 divided by L, so negative 6 divided by L squared, 2 divided by L, negative 6, that's the third row, so this is 12 divided by L cubed, negative 6 divided by L squared, negative 6 divided by L squared, 4 divided by L. Okay? Let me have those in some color. Let's have this in orange. Okay? So that's K1. Okay? What I did is just I copied, the member stiffness matrix that's going to be given to you on the test. Okay? Remember this. Okay? The member stiffness matrix. Okay? You're going to have this given on the test. This is the member, any beam member stiffness matrix looks like this. Okay? The only thing that you have to memorize is the arrangement here. What does each number here represent? I'm just going to give it to you, but you have to know what does each number represent. So it's arranged like this: delta, theta, at the near end, and then the far end. Okay? So start with the near end and then the far end. And delta and theta. Delta is first. Okay? So now, let's label those degrees of freedom here. This is how the stiffness matrix look like, but now what does those numbers represent? We are relating what degrees of freedom to what degrees of freedom. It's delta, theta at the near end, delta, theta at the far end of that member. So let's see here. Member 1. What is delta at the near end? 6. What's theta at the near end? 7. Okay? The degree of freedom number 7. What's delta at the far end? 3. What's theta at the far end? 1 or 2? 1. 2 is in member 2. Okay? So it's 6, 7, 3, 1. Okay? So those are the degrees of freedom here. 6. So this is 6, 7, and then 3, 1. 6, 7, 3, 1. So those numbers here represent, the unit displacements or the forces at those degrees of freedom due to unit displacements at those degrees of freedom. Okay? So that's K1. Okay? Now let's do the same for K2. Find the stiffness matrix.
Is there a reason why the rotation is 7?
Why the rotation is what?
7. 6 would be the reaction, with the 7 would be the rotation.
Yeah, this is, how the stiffness matrix is arranged. You have to start with delta and then theta, delta and then theta. Okay? You have to remember this. Okay? If you want to put theta first, that's fine, but you have to switch those two columns. Okay?
Yeah, that was the delta near, theta near. That's what you're talking about. Delta near, theta near, that's what you're talking about?
Yeah.
Okay.
So now, K1, now we're building K2, the stiffness matrix for member 2, okay? It looks the same, nothing changed, okay? It's the same EI, it's the same length, right? But what changes here? The degrees of freedom, okay? At the ends of member 2 is different. So what are the degrees of freedom at member 2? Delta, theta, and then delta, theta. What are those? Delta, theta at the near end is 3 and 2. Delta and theta at the far end is 5 and 4. So 3, 2, 5, and 4. Three, 2, 5, and 4. 3, 2, 5, and 4. Okay? So that's K2. Now, what's the third step? What's the third step? Just check your loads.
Build the overall stiffness matrix.
Exactly. Step 3. Build the overall stiffness matrix. So now, my question to you, how big is the overall stiffness matrix?
6 by 6.
Why 6 by 6? How many degrees of freedom you have in your problem? 7. You had 7 degrees of freedom, right? That's the first step that we did here. We said we have 7 degrees of freedom. That means that my stiffness matrix is going to be
7 by 7.
7 by 7.
That's what I'm going to say. That's what he actually said on the inside.
Okay, so K, the terms here, you're going to have EI, and it's going to be 7 by 7. So it's relating those degrees of freedom. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. Okay, so let's see, as an exercise, you tell me how to build this. How do you build this? How do you get this number? What do you call this? It's K11, right? How you get K11?
You look to see if there's...
You map it from the element stiffness matrices, from each member stiffness matrices. Is there K11 here? 1 and 1?
No.
And K2? No. Is there 1 and 1 here?
Yes.
How much?
4 over.
4 over L. Okay, let me just here, for your reference, let me change this color here so that, let's have it in green, okay? So you have the orange number here. It comes from K1, so 4 divided by L. Okay, and now 1 and 2. How to get 1 and 2? There is no 1 in K2 here, so for the first row, I'm not going to look for 1 here. 1 and 2, is there 1 and 2 here? No. No, so it's 0. By the way, but while building the first row, you can build the first column because it's symmetric, okay? The first row is going to look exactly the same as the first column. Now 1 and 3. Is there 1 and 3 here? How much is it? Negative 6 divided by L squared. One and 4. Is there 1 and 4 here? No, so it's 0. So negative 6 divided by L squared, 0. 1 and 5. Is there 1 and 5 here? No. One and 6. Is there 1 and 6 here? How much is 1 and 6? 6 divided by L squared. Does it make any difference when I say 1 and 6 or I say 6 and 1? They are the same. This is 6 and 1 and this is 1 and 6. They look the same, okay? Because they are symmetric, okay? So 6 divided by L squared. 6 divided by L squared. 6 divided by L squared. 7 and 1. Is there 7 and 1 here?
Yes.
How much is it? 2 divided by L. Now let's build the second row, okay? It's 2 and 1, 2 and 2, 2 and 3, and so on, okay? Is there 2 here? Is there the second degree of freedom here? No. So It's all going to come from this matrix, okay? 2 and 2. How much is 2 and 2? It's 4 divided by L. So now this comes from the K2. Oops. What happened? So K2 and 2 is 4 divided by L. Okay, 2 and 3. How much is 2 and 3? Six divided by L squared. And it's here as well. 2 and 4. 2 and 4. 2 divided by L. 2 and 5. 2, 5, negative 6 divided by L squared. Two and 6, there is no 2 and 6 here, so it's 0. 2 and 7, there is no 2 and 7 here, so it's 0. Okay? Now, the third row, 3 and 3. Let's see here. 3 and 3. We have 3 here, and we have 3 here. So I have to look in both matrices, okay? So 3 and 3. Here, 3 and 3, we have 12 divided by L cubed. So 12 divided by L cubed. What about 3 and 3 in the first matrix here? 12 divided by L cubed as well. Okay? So I just have to add the contribution from both matrices here. Okay, 3 and 4. 3 and 4, that's this term, 3 and 4, 6 divided by L squared. There's 3 and 4 in the first matrix here? No, so you're good. So here you just have 6 divided by L squared. Okay. What about 3 and 5? 3 and 5, I have negative 12 divided by L cubed. What about 3 and 5 here? Is there 3 and 5 here? K1? No. So that's it. So negative 12 divided by L cubed. 3 and 6. Is there 3 and 6 here? No. Is there 3 and 6 here? Yes, 3 and 6. Negative 12 divided by L cubed. Three and 7, there is no 3 and 7 here, but there is 3 and 7 here, negative 6 divided by L squared. And now the fourth row, 4 and 4. Is there 4 here in K1? No. So I'll just get all the numbers from this matrix only. So 4 and 4, I have 4 divided by L. So 4 divided by L. 4 and 5, that's 4 and 5, negative 6 divided by L squared. Four and 6, there is no 4 and 6 here. So it's 0. 4 and 7, there is no 4 and 7 here, so it's 0. 5, let's see here, there is no fifth degree of freedom is not here, it's only here, so 5 and 5 is 12 divided by L cubed. 5 and 5 is 12 divided by L cubed. 5 and 6, there is no 5 and 6 here, so it's 0 and 0. 5 and 7, there is no 5 and 7 here, so it's 0 and 0. And then 6 and 6, there is no 6 here, so it all comes from this matrix. 6 and 6, 12 divided by L cubed. So 12 divided by L cubed. 6 and 7. 6 and 7, 6 divided by L squared. And that goes here as well. 7 and 7, that's the last one here. There's no 7 here, there's only 7 here. It's 4 divided by L. Okay? So that's the overall stiffness matrix. We build it from scratch, okay? Just mapping the elements from each member stiffness matrix, okay? So now, did you need to find all those numbers? No. Why not? Which part? After finding this, you would subdivide this matrix into 4 different or 4 sub-matrices, right? What are those? Where would you divide this? Separating the known and the unknown degrees of freedom, right? The unknown degrees of freedom were the first ones, right? The first 4 ones. So you can count, just subdivide it here, 4 and 4. Okay? To find the displacements, okay, all you need is just this part. To find the reactions, you need this part. Okay? So those elements over here, okay, we just found them, but we're not going to use them. Okay? So maybe on the test, okay, if you're running out of time, you don't have to calculate this part. Just this
that
part.
one corner.
Hmm?
Just that one
Yeah.
corner.
This part is symmetric with this one, right? This part is equal to this, and this one is equal to this one is equal to this one is equal to this. So you want, put time calculating, if you just calculated this one is just the transpose of it, okay? So there is no problem. So what you need is just this part. Okay, those elements, 4 by 7. Okay? So you need those 4 by 7. So 28 elements that you have to find. But actually you didn't find all 28 elements, right? Because that was kind of symmetric. So you found those 4, and then those were symmetric, right? And then you find those 3, and those were symmetric, okay? So 4, 7, and then 9, and this was symmetric, 10. And here you found those, 3, so 13, and then you would find all of those terms here, so 13, 14, 15, 16, 17, 18, 19, 20, 21, 20. So you need to find 22 elements. Those what you actually need to find, okay? Not 28, okay?
So the first quadrant is displacements.
To find the displacements. So let's say on the test, I just ask you to find displacements. You don't need to find this part. This part is necessary if you need to find the forces, okay? The reactions. But if you just need to find the displacements, you just need the first part. The first part.
And
Okay?
what is this quadrant? The upper right?
This
I know.
one is symmetric with this one. They are the same.
So just find one.
Yeah.
And
Either find this one or this one, and the other one is the transpose of it. Okay? You see, it's the transpose. This one, this row here, is the same like this row, this column. And this row is the same as this column. And this row is the same as this column. This row is the same as this column. Okay? This part here is useless in this problem. Okay? We're not going to use it at all. Okay? This part, we're only going to use it in some other problem. We're going to see what other problem that you would need this part. But in this problem, you definitely don't need anything. Okay? So now, we found K. Okay? So actually, let's... This part here, although we found it, but it's not needed. We could have, not just not calculated. Don't put zeros, okay? It's not zeros, but you don't need it, okay? So on the test, if you put zeros, I will subtract points. If you just don't calculate it, I will not subtract points, okay? If you put zeros, it means that you understand it's zero. No, it's not zero, but I just don't need to know those values, okay? Any question? Okay, what about the next step then? Just look in your lecture. What did we do? What's the next step?
Load vector and displacement vector.
Okay, great. The load vector and the displacement vector. So, step 4. Calculate the load vector and the displacement vector. Why? Why do I need to find those? Simply, we need to write this equation. That's what you need to do. P equal Ku, the stiffness equation. This is the name of this equation is what? The stiffness equation, the stiffness method. Okay? P equal Ku. That's what you have to build. Right now, you already built K, 7 by 7. What's the size of P? The load vector is P. 7 by 1. What's the size of U? 7 by 1. Okay? So now let's build those P and U. So P, it has to be 7 by 1. Okay? So it's 7. The forces at the 7 degrees of freedom that we mentioned. Let's see, what are the forces applied on the beam at those 7 degrees of freedom? Let's go to the problem here and find the forces applied at the 7 degrees of freedom. The first degree of freedom is the rotation or the moment. Is there a moment applied on the beam here? No. The second degree of freedom is the moment here. Is there a moment applied on the beam here? No. Third degree of freedom is the vertical displacement or the vertical force. Is there a vertical force applied on the beam here? No, it's 0. So all of those are zeros. The fourth, is there a moment applied on the beam here? Yes, it's M node. Okay? And it's rotating in a clockwise direction, so it's negative. This is the fourth. What about the fifth degree of freedom? Is there a force applied on the beam here? How much is this? It's the reaction, Cy, which you don't know how much is it. Okay? The sixth. Is there a force applied here? Yes. How much is this? You don't know. It's Ay. Okay, the reaction, which you don't know its magnitude. The seventh. Is there a force here in the direction of the 7th degree of freedom? Yes, there is a moment due to the fixation, the reaction here, which is Ma, which you don't know how much is this as well. Okay? So just write those 7 forces applied on the beam, those 7 degrees of freedom. So the first was 0, 0, 0, 0, and then negative M node, and then Cy, Ay, what's this? 1, 2, 3, 4, 5. 4. Yeah. 4 is negative M node, and then Cy, Ay, and Ma. So those are known forces, right? You know the magnitude of the forces here. But those are unknown forces. Now U, the displacement, one, two, three, 4, 5, 6, 7. It will be the opposite. If those are known, so those are unknown. Okay? If those are unknown forces, so the displacements are known. Is it always like this? Yes. They are always opposite. If you know the force, you don't know the displacement. If you know the displacement, you don't know the force. Okay? So, the known displacements at the 5th and the 6th and the 7th degree of freedom, what are those known displacements? Delta C, delta A, theta A. They are all here. Okay? And the first 4 degrees of freedom are theta B left, theta B right, delta B, and theta C. Okay? So I'm just going to put those in the displacement vector here. So theta B left is unknown, theta B right, which is unknown, delta B, theta C, and then the rest are zeros. Okay? Now, what's next? What's the next step?
Put them together.
Yeah, write the stiffness equation. Which says P equal KU. So that P, the load vector that we just found, is equal to K. How much is K? That's K. Just going to copy it. Multiplied by U. You don't want to show this part?
So we don't need it, so we have to.
You don't need to calculate it. If you don't want to calculate it, just don't write it. No problem. Okay? So now you have this matrix, a set of 7 equations with 7 unknowns. How to solve this? What's the procedure? Procedure to solve this? You first solve the first 4 equations. So this is equal to this part multiplied by this vector. The first 4 equations only. Okay? So this is step 6 now, solving this equation. So step 6, solving the first 4 equations to find the displacements. You're going to find the 4 displacements. Unfortunately, in this problem, okay, since you're given the distance as L, you're given the moment as M node, you're not going to be able to use your calculator. You have to solve them by hand. Okay, the calculator, to use the calculator, you have to input numbers, right? So you have to solve them by hand. But if you have numbers, definitely you can just use your calculator. It's just going to do it for you so easily, okay? So theta B left is M node L divided by 2EI. Theta B is M node multiplied by L squared divided by 3EI. Theta B right is negative M node L divided by 6EI. So as you see, theta B left and theta B right are not equal to each other, okay? Theta C is negative 2 M node L divided by 3EI, okay? So now I solved for those unknown degrees of freedom. What else do I have to solve for? The reactions. How to find those reactions? Those are equal to this part multiplied by this part, right? Multiplication of matrices. Cy is this row multiplied by this column, right? So this 0 multiplied by theta B left. Negative 6L divided by L squared multiplied by theta B right. Negative 12 divided by L cubed multiplied by delta. Negative 6 divided by L squared multiplied by theta C. And then this term multiplied by 0. This term multiplied by 0, this term multiplied by 0. Since they are multiplied by 0, whatever value you're going to have here is going to be 0. That's why you don't need it, okay? At the end, you're going to multiply them by 0, okay? That's why we said you don't need them, okay? So, substituting those values into the last three equations, you get the values of the reactions. So Cy is going to be M node divided by L. AY is going to be negative M node divided by L. And MA is equal to negative M node. Those are the magnitude of the reactions here. Any question? Great. So now we said that this part you don't need it, right? In this problem. Is there a case where you would need this part?
They don't equal to zero. They don't equal to zero, those reactions.
If those are not equal to 0, right? But we're saying that this part is known, right? Can it be known but not be equal to 0? Did we deal with this before? Having
Displacement down.
exactly. So settlements of support or movement of support. If you have a movement of support, okay, you know the displacement, it's known, but it's not equal to 0. Okay? So that's where you would need that part when you have settlement of support. Okay? Those will be known, but they're not going to be 0. Okay? So that's what we're going to do now. Okay? Have a problem on the settlement of supports. So for settlements of supports, there is nothing new except that we're just going to add its value to the known displacement instead of 0. Okay? So let's see an example here. So in this example, we have a beam that looks like this. There is a moment here that is equal to 4 kilonewtons meter. There is a moment here that is equal to 4 kilonewtons meter. This is point A, B, C. Those lengths are equal to 2 meters, 2 meters, okay? And the problem statement says that for the shown beam with EI, here I have to give you the magnitude of EI. When there is settlement of support, EI has to be given because it's not going to cancel together, okay? EI is 4,400 kilonewtons meter square. We're required to calculate all the support reactions using the stiffness method if support B moves down a distance of 1.5 millimeters. So there is some settlement of support B. We understood previously what's the source of this settlement, a loose soil at point B and maybe hard rock at point A and C. So point C is going to move, there will be some differential settlement here between point B and point A and C, okay? So how to solve this problem? Nothing new, okay? You just have to follow the same steps, okay? So what's the first step? The notations. How many members do we have? How many nodes do we have? How many degrees of freedom do we have? And we have to label all of those. Okay? So how many members? 2. Member 1, member 2. Okay? The nodes, I have node 1, node 2, node 3. Is there any hinge, internal hinge here? No. That means that how many degrees of freedom you're going to have? 6. 2 at each node. Node 1, 2, 3. So you have 3 nodes. Each one is going to have 2 degrees of freedom. What are those degrees of freedom? A vertical degree of freedom, a rotational degree of freedom. Vertical displacement degree of freedom, a rotational degree of freedom, a vertical displacement degree of freedom, and a rotational degree of freedom. That's all. Okay? Now, those 6 degrees of freedom, I just have to label them. Okay? Definitely you can label them whatever you want, but we said the easier thing to do is you label the unknown degrees of freedom first. Okay? Which of those 6 degrees of freedom are unknown? Motion. Do you know how much is the vertical displacement here? Yes, it's 0 because of the support. Do you know how much is the vertical displacement here? Yes, it's 1.5 millimeters. Do you know how much is the vertical displacement here? Yes, it's 0 because of the support. Okay? What about those rotations? Do you know how much are those rotations? There is nothing preventing the beam from rotating at those points, okay? The only thing that prevents the node from rotating is what? Fixed support, okay? So those are unknown. The rotations are unknown, so I can label them 1, 2, 3. Someone would say, no, I want to label them 1, 2, and 3. No problem, that's correct, okay? 1, 2, and 3. Usually what I do on the exam, I label the degrees of freedom for you, okay? Why? To make grading easier for me, to be able to follow the numbers, okay? Because if I leave you to label them, I would, have the solution being 1, 2, 3, and you label them 1, 2, 3. You're correct, but I won't be able to follow your answer number by number, right? So I would label them to you, and that's actually beneficial to you as a student. Why? It's a hint, right? What are the unknown degrees of freedom, right? So 1, 2, 3, and then the the known degrees of freedom, I would label them here 4, 5, 6. Definitely you can label them anything, you can label them 4, 5, 6, stay correct, okay? So now I have 2 members. So how many element stiffness matrix I need to find? 2. I have 6 nodes, and I have, 3 nodes, and I have 6 degrees of freedom. So the 6 degrees of freedom, some of them are known and some are unknown. The first, the second, and the third degrees of freedom, okay, are unknown, and they represent theta C, okay, and theta B, and theta A. The rotation at point C, the rotation at point B, the rotation at point A, those are unknowns. And the 4th, 5th, and 6th represent the known displacements. The 4th is delta C, and it's equal to 0. The 5th is delta B, which is equal to negative. Why negative? Because it's downwards, and the sign rule for the stiffness matrix is upwards is positive, downwards is negative. Okay? So it's negative 1.5 millimeters, so it's 0.0015 meters for consistent units. And then the 6th degree of freedom represents delta A, which is equal to 0. So those are known degrees of freedom. So I have 6 degrees of freedom, 3 are unknown and 3 are known. Okay? So for the forces, that means that I'm going to have 6 forces, 3 of them are known and 3 are unknown. Okay? What's the next step? Members, stiffness, matrices. Here I have to build K1 and K2. So I'm taking EI as a common factor, and then you have to substitute the values of, the 4x4 stiffness matrix. Okay? So doing this, just substitute the numbers. It's going to be, this 12 EI divided by L cubed. L is how much? L is 2. So 12 divided by 8, 2 cubed is 8. So it's 1.5 and so on. So substituting those numbers is going to be 1.5, 1.5, negative 1.5, 1.5, and it's symmetric. The second row is symmetric with the second column, and then the third row is symmetric with the third column, and that's the stiffness matrix of member 1. Okay? All I need to do for this stiffness matrix now is label it. Stiffness matrix for member 1. What degrees of freedom does it relate? It's delta and theta at the near end, and then delta and theta at the far end. Okay? So delta and theta at the near end, and then delta and theta at the far end. So 6, 3, 5, 2. Six, 3, 5, and 2. 6, 3, 5, and 2. Okay? For K2, for member 2, it looks exactly the same. Why? Because it's the same length, the same EI. If it had different length, so the numbers will be different. If EI is different, then definitely the numbers will be different as well. The only difference here is what are the degrees of freedom these numbers represent. So for K2, okay, let's label it, let's throw it in a different color here so that when we build our overall stiffness matrix, we know where those numbers come from. What does those numbers represent here? What are the degrees of freedom for member 2? Delta, theta at the near end, and then delta and theta at the far end, right? So what's delta here? Start with 5, 2, 4, and 1. Okay? 5, 2, and then 4 and 1. Five. What would you do next? The overall stiffness matrix. Build the overall stiffness matrix. How big that's going to be? 6 and 6. So K is going to be 6 by 6. We have EI here. It's going to look like this. 6, so you have 1, 2, 3, 4, 5, 6. By 6. 1, 2, 3, 4, 5, and 6. Okay? You build this one by one by mapping the numbers from the two elements stiffness matrices. Okay? So doing this is what we're going to have. We're going to have 1 and 1 from member 2, 1 from the element 2, 0, negative 1.5, 1.5, 0. And that comes here as the first column as well. And then for the second row, you have 2 from member 2, and you have 2 from member 1. You have 1 here. You have negative 1.5 here. You have 1.5 and 1.5 from the other stiffness matrix. Here you have 1.5. For the third row, you have 1 and 2, and this one is 0. It doesn't have any contribution from any of them. Negative 1.5, 1.5, and this is the third row. The second row column here becomes negative. This is the second one, negative 1.5, 1.5 plus 1.5 and 1.5, and then here you would have 0, negative 1.5, 1.5, and then for the fourth you have 4 and 4, you have 1.5 here. Negative 1.5 and 0, so negative 1.5 and 0. And then for the fifth, you have contribution from both matrices, and negative 1.5, negative 1.5.
Shouldn't 5 and 2 be negative 1.5 plus 1.5?
5 and 2. Yes, this is negative, so 2 and 5 is negative as well. Okay? And this is in green. Okay? So this is the overall stiffness matrix. You need to subdivide it. Right? Where? 3 and 3. So you would subdivide it here.
Does that go down
Yes. Okay? So you need this part to find the displacements. You need this part to find the reactions, right? Now we had 1 degree of freedom that was known, but it was not 0, right? What was that? The 5th degree of freedom, right? You knew the displacement at point B was equal to 1.5 millimeters, right? That means that the values here on the 5th column, all those values are needed. You need all those values.
So it has to be the column?
The column is symmetric with the row, right?
Oh yeah, you're right.
But the values for the 5th degree of freedom, the 5th column or the 5th row, you need all those values. Why? Because they're not going to be multiplied by 0. They're going to be multiplied by the 1.5 millimeters. Okay? So they don't cancel here. So now what's the next step? So here you don't need those values. You don't need those or those. Okay? But out of this part, you need those values here. Those 3 values are needed. Then those and those are not needed, as previously. Okay? Now you need to find what? What's step 4? Load and displacement vectors. And let's add step 5 and build P equal KU. So what's P here? P equals KU. What's P? The forces at the degrees of freedom. Having those, what's the force here at the 1st degree of freedom? What's the force here? 4 kilonewtons meter. Is it positive or negative? It's rotating in a counterclockwise direction, so that's positive or negative. You have to remember the sign convention, sign rule for the stiffness method. Counterclockwise is positive. Okay? That's opposite to the slope deflection method. Okay? I'm not the one who chose those sign rules, okay? Just following them as used. So don't blame me that you have, I'm getting confused, okay? I didn't choose those, okay? So it's 4 kilonewtons meter. And then at the 2nd degree of freedom, how much is the moment there? Is there a moment here? No, it's 0. The 3rd degree of freedom, that is this moment. How much is it? It's clockwise, so it's -4. The 4th degree of freedom, what's the force here? Cy, the reaction Cy. The 5th degree of freedom is the reaction By. The 6th degree of freedom is the reaction Ay. Okay? So let's build this stiffness matrix. The load vector now. So I have 4, 0, -4, and then Cy, By, Ay. The first 3 are knowns, the second 3 are unknowns. K is Ei multiplied by this matrix here. That's K. And then I have to multiply this by U. The first 3 are the unknown degrees of freedom, which were theta C, theta B, and theta A. And then the known degrees of freedom, we had 0, and then we had negative 0.0015, and then 0. That was the settlement of support B over here. Okay? That's the settlement of support B. Okay? What do you have to do now? Solve the first 3 equations. So now let me help you doing this so that you don't, so this is the next step here. That was step 4 and 5, okay? Now step 6. Solving the first 3 equations. How does this look like? You have 4, 0, negative 4 equals EI multiplied by this matrix here. 2, 1, 0, 4, 1, 1, 2. Okay? I'm just copying this. 2, 1, 0, 4, 1, 1, 2. This is multiplied by this, okay? Vector. Theta C, theta B, theta A. Theta, sorry, C, theta B, theta A. That's what we did in the previous problems. But now you have this part multiplied by this part, right? Previously, this was 0, so the multiplication of this by 0 was 0, right? Now it's not 0. So you have to multiply this one by this one, which is 0, and then this one by this one. That's why I need this factor here. 1.5, because it's going to be multiplied by the negative 0.0015, okay? And then on the second row here, you're going to multiply this by this again. And then for the third row, you're going to multiply this number by this number. Okay? So I have to add those to the equation. 1.5 multiplied by negative 0.0015, negative, which is 0, this term here is 0, multiplied by this, and then negative 1.5 multiplied by this. Okay? So the values on the 5th column, I have to add here the values on the 5th column, which is 1.5, 0, negative 1.5, multiplied by the settlement of the support, okay, which is negative 0.0015. And there is EI here. When you multiply those, all the elements here have an EI factor, right? Now just substitute the magnitude of EI and solve this equation, okay? So you want to use your calculator, okay? So here you can move this, okay, to that side of the equation, so you just have a matrix form, right? Not an addition. Here you have some addition. So you can move this here and add it to this part here. This is in positive, so you subtract it from here. Okay? I just want to write it in a matrix form. So therefore, here I have 4. And this is a negative sign, so this becomes 0.0015 EI multiplied by 1.5. Here you have 0 and then 0. Negative 4 minus 0.0015 EI multiplied by 1.5 equals EI multiplied by that matrix You understand what I did here? I just moved this here. It was added to this side. I just subtracted from this side here to get this vector. Okay? Why did I do this? So that I can use the calculator to just input this matrix and solve it. Right? Instead of having addition, it's again just a vector equal to the matrix multiplied by a vector. Okay? Now you can use your calculator and solve those values. So solving, you would find theta A and theta B and theta C. They're going to be in terms of EI. So those are going to be 0.00158 radians and 0 radians and negative 0.00158 radians, and then substitute that the last three equations. So Cy, how much is Cy? Cy comes from multiplying this row by this column. When you multiply this row, you're going to multiply this by theta C, which you found, this one by theta B, which you found is 0, this one multiplied by theta A, this one by 0, this one by this value. Don't forget this, okay? So Cy here, you have EI, and then you have negative 1.5 multiplied by theta C, negative 1.5 multiplied by theta B, and 0 multiplied by theta A, and EI multiplied by negative 1.5 multiplied by 0.0015. So that's equal to negative 0.525 kilonewtons. Doing the same for BY, 1.05 kilonewtons, and AY is equal to negative 0.525 kilonewtons. Any question? Just 1 minute, okay? Is this the best way to solve this problem if you have it on the test? It's easy, it's not hard, by the way, but it's not the best way. Why not?
It's symmetric.
It's symmetric. You could have made use of the symmetry, okay? As you did with the slope deflection method, just solve half of the beam. It's symmetric about support, okay? So you can just remove the middle support and substitute it with a fixed member, right? And still keep the deflection, the settlement of the support right in the middle, okay? So it's just keep the rotation at the midpoint equal to 0. That's actually what you got here. Theta B is 0. And this rotation is equal to the negative of that rotation, right? So you could have made use of the symmetry. You would just have one member to solve, okay? So the overall stiffness matrix would be the same as the element stiffness matrix because you just have one element. So it would have been much, much easier if you made use of the symmetry, okay? Any question? Okay, so see you next week.